Hello, I'm Gil Carlson, Director of Technical Services for ITT Fluid Handling Division. This discussion will involve selected parts of an article printed in 1971 in Heating, Piping, Air Conditioning. The article still pertains, however, in terms of basics to the design and application of pumping systems for heating, cooling application. One of the parts involved in this had to do with decreasing flow rate through existing hot water baseboard systems in order to decrease pumping power. And let's illustrate the derivation of this application. In this illustration, we're showing baseboard terminal units. The conventional design for baseboard terminal circuits systems has to do with a 20-degree temperature drop. The use of a 20-degree temperature drop as a design tool for baseboard systems, hot water systems, has to do with the fact that at a 20-degree temperature drop, 1 gallon per minute flow rate equates to 10,000 BTU per hour conveyed in the piping system. It has no true relationship to overall system design, except that it's a very convenient approach in terms of design. In terms of the baseboard terminal units, so long as we provide a consistent mean water temperature through the terminal units, we will establish the same heat transfer capability. In the first illustration, we have 210-degree supply water temperature, 190-degree leaving water temperature, and a 200-degree mean water temperature in the terminal unit. And this can equate then to a basic flow rate at 10,000 BTU of 1 gallon per minute. Now, supposing that we were to increase supply water temperature by 10 degrees up to 220, decrease the flow rate, and provide an exit water temperature of 180 by decreasing the flow rate to 50% of design or to a 40-degree temperature drop. We would still maintain the 200-degree mean water temperature and therefore establish the same terminal heat transfer output, but we would have reduced our flow rate by 1/2, and in the existing piping system, we would have reduced the head loss by 1/4, because head loss in the piping system will vary as the square of the flow change. So we will only need 1/8 the power requirement for that piping system. The reduction of flow rate in the existing piping systems works well, but we must concern ourselves as we modify these existing systems to decreased flow rate to the increased potential for trouble through flow balance. Providing we provide the necessary flow balance in the existing system, we will work quite well. It should be remembered that the 20-degree temperature drop design system overcomes, because of very high safety factor, a good deal of trouble potential from a lack of flow balance. And this is in truth due to the fact that decreased flow rate in these systems will not markedly affect the mean water temperature and therefore will not markedly affect terminal heat transfer output. However, when we reduce our flow rate by 1/2, we can introduce potential problems in terms of circuit flow balance. So we can, for many of our systems, reduce flow rate to 1/2 of that originally intended, and because of this, finally reduce our power input to the order of 1/8, providing again that we have provided the necessary flow balance. Let's then consider another aspect as originally described in the reprint available to you, and that has to do with zone pumping. Zone pumping has high potential in terms of pump energy saving. And this very simple illustration describes a single pump used to flow water through one circuit which has a high flow rate need but a relatively low head loss need. The second circuit has a relatively low flow rate need but a high head loss need. This would then establish that the pump is basically sized in terms of flow by the high flow need, but in terms of head is selected in terms of the high head loss need for the high head loss circuit. We can then establish that this pump must provide 200 gallons per minute, the summation of 150 plus 50 gallons per minute, and will be required to provide the necessary head for the high head loss circuit, which is 60 feet of head loss, plus the head loss common to both circuits in the piping common to both circuits of 10 feet. No, this is 50 feet. So we have a total pump head need of 60 feet at 200 gallons per minute. Now we can equate through the basic pump energy power relationship that flow and head are the predominant factors in terms of establishing pump power draw. So in this circumstance, we can take flow times head and establish a number that is truly relevant to power consumption for this system. So we have 200 gallons per minute times 60 feet. Or we can establish a flow head power draw of 12,000 GPM feet. Let's take this same system then and consider it with two pumps, each his own pump, and each pump flowing its own circuit. The first pump would flow 150 gallons per minute at a 20-foot head loss through its circuit, but will require, in addition, 10 feet of head loss for that piping which is common to both circuits. So that pump will be 150 GPM at 30 feet of head. And we can establish a GPM flow head power draw for that of 150 times 30, or 4,500 GPM feet. In the second circuit, we have a need for 50 gallons per minute at 50 feet of head, adding to that the 10 feet of head necessary for the piping common to both circuits, and we will establish 60 feet of head as the need for that pump. So 50 times 60 is 3,000 GPM feet. We wind up then with 7,500 GPM feet as the total power need in terms of water flow for this piping circuit. This is contrasted with the 12,000 GPM head requirement for a single pump. Should be noted, however, that when we zone pump, we can introduce potential problems. And the potential problem is caused by the pressure drop in the piping common to both circuits. For example, if we have a variable head loss in that common piping, as from a single strainer, we can cause trouble if that strainer becomes clogged. This is because the common piping head loss is common to both pumps. And should that strainer become clogged, a check valve installed at the discharge side of the low head pump may close because of back pressuring through the clogged strainer. Now, unfortunately, it has been found, after long and serious study, that a single strainer costs less than 2 strainers. And more than that, the strainers are usually supplied as very fine mesh. The strainer could become clogged on a very, very cold night where this pump is serving a terminal air handler in a gymnasium which has just been refloored. And if that pump stops, the terminal air handler could freeze, causing great damage in terms of that gymnasium. It's important to remember that the piping common to zone pumps should be installed in such a way that the piping pressure drop from A to B is consistent at all times, and there is no potential for an increase of pressure drop in that common piping to cause one of the zone pumps to have its check valve close during any time. Another problem that occurs is that if this system included a boiler, for example, with a resetting 3-way control valve for reset of water temperature, and if that reset were accomplished by 2 butterflies, as illustrated here, the butterfly control valves will, under a 50% flow condition through the reset of that valve, establish 4 times the head loss that would occur if flow occurred only through one valve with the other valve closed. So we can run into a condition then with butterflies where if the valves close off or go to a 50-50 position, we can again establish a very high back pressuring against the low head loss circuit, which will cause a decrease of flow rate for one thing, and under certain particular circumstances will close that check valve so as to potentially allow a freeze up in the piping circuit. Again, in zone pumping, it is necessary to maintain a consistent common pressure drop through each of these circuits. Primary secondary pumping in the equipment room will eliminate a great deal of the otherwise difficult problems associated with zone pumping. This is because in primary secondary pumping, we would establish flow rate as through boilers and chillers through a section of piping in that piping common to both zones through a very low head loss common piping section. We can then provide a separate pump, but establish at all times then that the pressure drop from A to B will be consistent and will not change despite changes in the reset scheduling, for example, of a boiler, in which the reset valve is placed in this circumstance in the secondary circuit, so that we then have that single consistent head loss from A to B. Another point is that any strainers placed in the piping common to both circuits should be very large mesh, as utilized in our roller troll air separator. This then places the compression tank and the roller troll separator at the suction of each of the zone pumps. Now, should fine mesh strainers be needed for the protection of control valves, etc., in the secondary circuits, we would place those fine mesh strainers at the discharge of the pumps. This would eliminate again the change in head loss in the piping common to both zone pumps, which can cause difficulties and could cause the check valves, the discharge of each of these pumps, to close, given a very substantial change. Zone pumping is also applied to very, very substantial systems and is used as a method of reducing power consumption. This illustrates a system in which we have a pump requiring 148 brake horsepower, principally because one of the zones pumped by that single pump requires a head loss of 100 feet of head, even though its flow rate in terms of percentage of design flow provided by the single large pump is very low. Now, we can take that single zone and separately pump it. And if we separately pump it, we can remove the 100 feet of head in terms of requirement from the major pump in the equipment room and substitute the smaller pump for that high head loss circuit. This is illustrated in this example, which utilizes primary, secondary pumping. And in primary, secondary pumping, which will be explained in greater detail, we utilize common piping as the interconnection between the secondary zone and the primary zone. We can then utilize a small pump to circulate the separate zone, utilize the major pump for circulating the other zones, but decrease our pumping power draw very considerably from 148 horsepower in this example down to 87 horsepower. Of course, we must add to the 87 horsepower need for the primary pump the 18 horsepower need of the secondary circuit. So we would have then 87 horsepower for the primary pump plus 18 horsepower utilized in the secondary circuit. And we would have 105 horsepower total pumping need for this system, as contrasted with the 148 horsepower originally established as the horsepower need when we had only a single pump and that single pump was forced to utilize a great portion of its head in terms of circulating the high head loss circuit. So we are then saving 43 horsepower during the operating time of this system. And you can see what has happened is this, that we have utilized a small pump to reduce head for the large primary pump, resulting in a very substantial power saving. Now, at $500 per horsepower per year, if the system ran during the entire year, we would be saving $21,500 per year by simple installation of the pump in the secondary circuit. Let's introduce another subject having to do with zone changeover. In this illustration, we have a single pump driving flow through each of two circuits and through the equipment room. The equipment room contains a boiler and a chiller. The chiller has a relatively substantial head loss of 30 feet. But the point is this, that the single pump being employed for this system must, during the wintertime, when needs in terms of head loss through the boiler and its resetting control valve is low, must provide and work with the head need of the chiller, even though the chiller is not in operation and valved off. In addition to this, the need for flow during the wintertime is very substantially reduced in comparison with the need for flow during the summertime. So let us, as a first example then, simply replace the chiller in terms of replacing that with a primary secondary design. We can then provide a pump which will circulate the chiller alone during the summertime. And because we have now removed the head requirement for that chiller, we can very substantially reduce the head need for the main distribution pump. In this case, we're saving, for this example, 11 horsepower